It's again a pleasure to me to introduce Babak Haghighat, who will be talking us about irregular Kac-Moody representation, physics homological equation, and Gaiotto-Teschner modules.
Thank you. Thanks very much to the organizers for the invitation. It's great to be here, to be back. So yeah, this is indeed work on all these three things, and it's based on two papers so far, and with varying authors, but they include Sergei Gukov, Ihua Liu, who was my student, he just graduated, and Nikolai Reshetikin. And so last year I was here already, and I talked about the first paper, and in the meantime we had another paper. So this will be a continuation of last year's talk. So in that sense, there will be at the beginning maybe some overlap, so I hope that's fine. But then later on there will be some new results. So good. So let me begin. So the papers are, I didn't give the archive numbers, but you can find them. So let me begin with the motivation. So it's basically twofold, and the first part is the AGT correspondence. So so this is a 2D, 4D correspondence, and we will be interested in irregular operators in Liouville theory. And the reason is that if you look at 4D n equal to 2 Argyll-Douglas theories, then you will you can actually obtain them by studying Liouville theory with irregular operators. So 4D. This is a little bit. Okay, I broke it, but it's still. It's better? Okay. So they give rise to 2D Liouville with irregular operators. So in that sense, it's important to study these for studying these theories, and also I'll be including the generate operators so that one can study actually surface defects in these theories. And the second motivation is basically from a 3D perspective. So there will be topological phases of matter. So it's still, maybe break again. Better? So here we can of course compute so wave functions of such topological phases of matter are in universality classes, which are described by conformal blocks of 2D CFDs. Basically, they're chiral versions. And so the basic question here is, so these are, in a more mathematical language, these are TQFTs, topological quantum field theories. They will describe these types of topological phases. And wave functions are described by conformal blocks. So wave functions of anyons are described by conformal blocks. And then there is the basic question of what happens if we include irregular defects. So there is this question. What happens in the presence of irregular defects, and how do braiding properties and associators and so on which basically capture these TQFTs change. So I won't enter this part, but one basic building block which is important for this part are these KZ equations, and this is something I'm going to derive in the presence of irregular operators. But the main focus will be actually on Liouville conformal blocks and irregular Kac-Moody representations. And therefore, I will start with some background, namely on Liouville theory. Okay, so yeah, before I go to that, I hope these topics are clear. Otherwise, if there are any questions, please ask any time. So,
these are 3D TQFTs.
Right.
Where the surface is the boundary.
Exactly. So you basically have some sort of 2D surface, and you can describe some adiabatic motion and time, and you have some primaries which are or anions, and they can braid, and so on and so forth. And you can have some sort of irregular defect somewhere, and then you can ask what is changing it. So, right. So okay. So as I said, we will consider 2D Liouville theory, and the classical action will be yeah. So sigma chi. And you're gonna have also the Liouville term. So it's this form. And so this is classically the theory, but if you quantize upon quantization, you basically, this theory will flows to a 2D CFT. So by quantization, I mean that you compute the path integral with e to the s over h bar, and here you identify h bar with b square, where b will be a complex parameter. And then the 2D CFT will have central charge 1 plus 6q square, where this q is 1 over b plus b, and you will have also conformal primaries, which will have a continuous label, which is known as Liouville momentum. So their conformal weight is depending on this Liouville momentum alpha, and it's given by alpha times q minus alpha. And this alpha is also in C. So these will be the conformal weights of primaries. Okay, so this is basically yeah, the general setup, but we are going to be interested in so-called degenerate operators. Apart from irregular operators, which I'm going to describe, we'll be interested in degenerate operators, and their alpha will take some discrete values. So let me describe that. Oh, I can also use this one, or is it preferred? Maybe the first half here is good. Okay. So the corresponding, okay, here I should also say that there will be corresponding vertex operators. You cannot see here. So you want me to use this one purely? The others can see? Okay, then we just stay here. Okay, so there will be, of course, vertex operators by the operator state correspondence, and here you will have some V alpha, which is given by e to the 2 alpha chi, say at some point z, and normal ordered. So these will correspond to the states which will have these conformal weights. Now there will be the generate operators. And here, yeah, let me call them V r comma s, or let me like this. And these are operators of the form where you have something like r minus 1, b plus, or 1 minus r, sorry. And you have 1 minus s, 1 over b, and they are defined in this way, where r and s are some integers. And there will be the generate because they will, corresponding primary states will admit a null state at a certain level. So in that sense, if you have an insertion of such an operator, this typically leads to BPZ type equations where the conformal block satisfies certain differential, depending on the order of the null state, higher order differential equations. Okay. So this is so far the story. So I want to be very brief because I want to jump into the irregular story, and that's still a summary, and then we will go to Kac-Moody representations. So any questions about the basics before I go to the irregular part? Okay.
So that you read symmetry changes R and S.
Or B to 1 over B. Yeah, R and S. Exactly. Exactly. Yeah. Yes, you're going to have many redundancies because many operators will be mapped to each other. Yes. Okay. So now this is the part 1. So here we want to look at irregular states. And these are irregular states, or irregular, if you want, representations of the Virasoro algebra. Okay. So let's look at the simplest case of rank 1. So there will be a rank 1 irregular singularity, and here you will have that Lm acting on the state. So the state will be parametrized by, I stands just for irregular, and it is parametrized by some complex numbers C and alpha. So the C is not to be confused with the central charge, that was C hat. But these are 0 for, obviously, usually for any regular representations, there would be 0 for any positive m. But here there will be 0 for, say, m greater than 2. Then you're going to have L2 acting on it. And here you will have something like minus C squared over 4. And you have also L1, which is non-zero, which is very unusual. And here you have C times Q minus alpha. And you have L0, which is C del C plus delta alpha acting on this state. So you see already that this guy acts non-diagonally. So you have to differentiate. You have to take this logarithmic derivative with respect to this parameter. And if C is 0, it acts just like an ordinary you basically retain the ordinary representation, the regular one, where this will be a highest weight of Liouville momentum alpha, and these guys will also vanish as they should, right? But if C is non-zero, you see that the whole thing is deformed in this way. And this can be, of course, extended to, higher rank. So if you have, let's say, rank R, then you will have non-zero entries here up to L2R, and then the above guys will annihilate the state. So in that sense, I want to focus on this simplest setup, and of course it can be all generalized to arbitrary rank. Now, yeah, as I said, alpha is just Liouville momentum. And C is some constant, so some arbitrary. And there will be also a vertex operator. So the corresponding vertex operator is basically 2 alpha chi at some position L. And you're going to also have then something like C del chi. And you take, you can insert it at infinity by sending this L to infinity. And this will be the corresponding operator for this state. Okay? So that is what is the definition of these irregular states. And you can obtain them from regular states by in a collision limit where you take two primaries and collide them in a double scaling limit where you send the distance to 0. Let's say you have some primaries with alpha 1 and alpha 2. You send the distance to 0 and these alphas to infinity while keeping the sum constant. And then you will obtain, you can show that there is indeed a well-defined limit where you obtain these types of vertex operators and giving rise to these representations. So these are perfectly present in Liouville theory because it has a non-compact spectrum. So you can do this. You can send the alphas to infinity. And so it's all fine. Okay. So this is so far just briefly what these irregular states are, because I don't want to go too much into the representation theory here. This is all well known and well studied. But are there any questions so far about this? Okay, so then I will go to integral representations of these of the corresponding conformal blocks with, say, one irregular operator and several degenerate fields. Okay, so this will be the next thing. Yeah, since I'm not using this board, I'll have to erase here. Okay. Yes? Yes, questions? Mm-hmm.
Quickly comment on the AGT interpretation of this parameter.
Right. So if so what happens if you take, let's say, take the 2 sphere with one such irregular operator, and it has to be at least of rank 2, and say one or more ordinary operators, then you can get certain Argyros-Douglas theories, and some of them you can get for when you have just one irregular operator, but then the rank has to be very high. So 7, 8 or something like that. I don't know, but there is a nice table, maybe in their papers, and you can look it up. So this is, so that would correspond indeed to these, so these conformal blocks with the correct rank and correct other operators will indeed give rise to some 4D Nekrasov partition function. Whereas B square will then correspond indeed to, let's say, from the Nekrasov parameters will correspond to the ratio of epsilon 1 and epsilon 2, this kind of stuff.
With the rank 1, could you pair it with some other vertex operators?
Rank 1, I'm not sure. I think you have to go to higher, as far as I remember. Yeah.
Those things are very something like NF equals to 2. Yes, NF equals to 2.
The rank 1?
Yes,
Two such operators, right. You have to do at least two or higher rank. Yeah. Mm-hmm. Okay, so let me go to the corresponding conformal blocks, and there, what I will be interested in are integral representations. Okay, so here we have to introduce screening charges, as usual, to do the Coulomb gas formalism. So we introduce screening charges at some positions, Wi in C, and these screening operators, I will only consider a particular type, as you will see in the following. So now we look at conformal blocks with the generate operators, if you want V minus Ka over 2b, and these Kas are some integers. So you see, I'm just taking the degenerate operators with 1 over b, the ones with b, the corresponding value is set to 0, so it's just parameterized by one integer as contrasted to before when we had 2. So then the corresponding conformal block will depend on some integration cycle, but it is basically the integral of let's do it in this way. So you have the product over all these screening operators, and you have the product over these degenerate operators at positions ZA, and you have some irregular operator at infinity. So you evaluate this correlation function in the free theory, and you can obtain the depending on these. Of course, here you have to take the measure as well, and you will have to integrate over these integration cycles where the sigma here. So this is a so-called Lefschetz thimble, and the sigma is so if you take this whole thing and evaluate it by Wick contraction, you can actually write it as the exponential of 1 over b square of some w, and this w depends on the za and this wi, and this is known as the superpotential because it also has a Landau-Ginzburg theory interpretation. So these sigmas are just critical points of this superpotential w, critical with respect to the w variables, okay? And so for each of those, you're going to end up with some steepest descent contour, which leaves this critical point and kind of goes to, these contours are parameterized by some parameter, where at infinity at both ends, this w here, this 1 over b squared w will go to minus infinity. So there will be some contours which are kind of like this, where at these two ends here, so that you will have some critical point somewhere here, but then, or critical value, but then at these points, this w over b squared goes to minus infinity, so that the integral is well defined and converges and so on and so forth. The real part, right. So the real part here will go to minus infinity, right, so that it's converged. So this is basically what I call this gamma here, the cycle gamma, and so they exist, and you can then, depending on the number of screening charges, compute them. And the other screening charges excluded, so we also have screening charges which go with V of B, but we don't need them because these guys, we excluded the guys which just have those operators which just have B in the numerator. So these are the only screening charges needed, and you have to satisfy charge conservation. So the sum of all these charges has to be equal to Q, and this is how you can basically, this gives you a constraint, but then it gives you also the number of necessary screening charges and so on for a given set of operators here. Okay. Now you can compute this easily, and computing the Wick contractions, and then you get the integrand, and from that you can extract the superpotential, and the whole thing will look as follows. So let me write it down. Yeah. So we basically compute that this whole thing in these brackets, this is basically, well, maybe there are some proportionality factors, but there is a product over ij, wi minus wj to the power of minus 2 over b squared. Then there is a product over I and A, wi minus the za, and here you have ka over b squared, and you also will have something like ab za minus zb, where you have minus ka kb over 2b squared. But then you will also have some all the Wick contractions with this irregular operator, and if you evaluate those, you will end up with something like this. So you will have the sum over I and wi, and minus 1/2 sum over A. Well, I think it's basically ka za. Okay. And this lambda here, it just appeared out of the blue, but we have kind of identified this parameter c with lambda over b, and then you will get these kind of you basically get, as I promised, you can factor out this 1 over b square, and then you have this superpotential which will be logarithmic. So this part will be purely logarithmic in these variables, and this part will be polynomial. So this is basically the part which gives rise to the irregular properties. And so this, if you wouldn't have this, then this would be these integrals would be of hypergeometric type, but these will just modify it, and you can also include, higher rank irregular operators, and then you will just get higher powers of these variables here. Okay, so and they will be basically resulting in some also geometrically in some irregular singularities at these points. So this is basically what I wanted to tell you or recap about these irregular Liouville conformal blocks. And now in the next part, I want to connect these actually or rederive these from irregular Kac-Moody representations. So this will be kind of what we did in the new paper, and I want to focus on that. But before I go to that, any questions so far? You mean alpha here? This alpha is fixed by charge conservation, basically. So it's not a free variable. Yeah. Good. Okay. So then let me actually proceed by doing the irregular Kac-Moody algebras, if there are no questions. So. Okay, so. Okay, so here, what is the idea? We want to use the following correspondence. Namely, on the one hand side, you'll have, the 2D Liouville CFD, and this is basically parameterized by this, or fundamental parameter is B square. And then the other side, you will have the non-compact SL2C WZW model. So obviously here on this side you have a current algebra, and this is of course also depending on this level or quantum level kappa. So there will be a correspondence also between these levels, and so the idea is use this picture and the corresponding Kac-Moody algebras there to see how one can construct actually irregular Virasoro representations using the Sugawara construction. So, and the strategy will be Fock space using Fock space representations. So use Fock space representation of the following Heisenberg algebra of the bosons. So you're going to have alpha n with n in Z, and you're going to have commutation relations alpha n, alpha m is equal to n times delta n plus m. And we will look first, to begin with, at regular and irregular representations of these bosonic modes here. And from that, we will then proceed to generalize to the SL2C case, and then see how those are connected to the representations I was talking about before. So, yeah, so this is the main idea here, but now let me come to the representation theory. Okay. Okay, so now let us look at regular representations, and then from there, good. So the way we will approach this is we choose our Fock space as a polynomial ring. So call it H, which is the space of polynomials in variables x1, x2, and so on and so forth. And then we choose a vacuum V, which is in this space. Okay. And we have the usual representations. Okay, let's just do n greater than 0. And you have alpha minus n is just xn d. Yeah, it's basically a gain for n greater than. So these are the usual representations. You will see that these guys, if you choose, let's say, v to be 1, so choose v to be just the the ray given by C, or by 1, multiplied by C, you will see that these will annihilate it. So, and it will be a highest weight state, and then you will get these descendants, and they will be all landing in this polynomial ring. Now, so there will be the corresponding module, which is the induced module of all these modes where these alphas are smaller than 0 and induced by acting on this V. And if you call this module, let's say M, then this will be basically your regular representation. Now the irregular representation is Sure, yes. So the irregular case, you will have the same. So you will have alpha 0. Irregular is equal to lambda irregular. You have alpha n. And this is n irregular, n greater than 1 now. And alpha minus n is xn, n greater than 1. And alpha minus 1 will act now non-trivially in this way. So this is very different because the negative guys acted by multiplication, but here we have differentiation, and alpha 1 is just minus x1 v irregular. And then one can basically proceed to choose now v irregular to be 1 over square root of x1, and then you will see that via the and you can also choose an energy momentum tensor of this form. So you can choose just 1/2 alpha z plus theta alpha z. And then you will see that indeed the corresponding modes will act in an irregular representation of the Virasoro algebra, as discussed before, by introducing kind of these swaps here. Okay, so this is just a basic example how to construct these irregular representations from the Kac-Moody algebra. And now I want to go to the SL2 case, which is the central representation I want to look at. Okay, so now we're going to go to SL2C. And here we will use, for the energy momentum tensor, this one. So this is the car time generator, and then you have lowering and raising operators. And in this way. And yeah, here this piece I can define as kappa. And I can also introduce now some beta gamma system. So here you have beta n gamma m is delta n plus m. So I'm introducing further modes, beta and gamma. And so these will be sum over n beta n z to the minus n minus 1, and gamma is sum over n gamma n z to the minus n. And E of z can be then represented as beta h is then minus 2 gamma z beta z plus 2 kappa alpha z, and F will be minus gamma square z beta z normal order plus square root of 2 kappa alpha z gamma z plus k d gamma d z. So if you use this representation with these modes beta and gamma together with the alpha modes from before, you will indeed obtain the correct SL2 algebra, or the correct OPEs, and then this will be your energy momentum tensor. So now we will have to study irregular representations of these modes, and which will give rise to the corresponding irregular representations of the Virasoro algebra, which we studied before. And this is actually also simple. So we will have, we'll choose regular representations for beta and gamma. So we will have beta n is del yn. So let's call this so this is how they will act on states when n is greater or equal than 1. Beta minus n will act as Cn, and this is for n greater or equal than 0. Gamma n will act as minus del Zn. And no, so this one is actually 1. No, this was also 0. And gamma minus n is yn acting by multiplication, but now n is greater or equal than 1. And you see that here the action of this beta gamma system is regular, so you will have highest weight representations, because if you choose the vacuum, say, to be 1, it will be annihilated by these, but these will just create further states. So beta gamma act or regularly, we say. But then we want to keep alpha irregular. So this is the crucial point. So we will keep alpha irregular as before, but beta gamma will act in this regular way. So all these, as you can check, all these operators will have the correct commutation relation. So those will be representations of this algebra, and alpha, even if it acts irregularly, it will furnish a representation of this Heisenberg algebra I had at the beginning. So these are perfectly fine representations. They only act differently on the vacuum state. And then we're going to choose the vacuum state to be the gain of this form. And what you obtain is the following action. So L0, using the Sugawara construction, so using this energy momentum tensor, and plugging in all these things, you will see that this will act as x1 d dx1 plus lambda square over 2 minus theta lambda acting on V, and L1 is minus x1 lambda minus 2 theta V, and L2 will be 1/2 x1 squared V, and Ln V will be 0 for n greater than 2. So if you now compare this with these irregular representations I had at the beginning, you will see that we just have to identify these things, these parameters correctly. In particular, x1 can be identified with I times c, or the other way around, and this theta can be identified with q, and this lambda can be identified maybe up to sign with an alpha, and you will see that you get, in fact, the corresponding irregular Virasoro representation. So let me write it down. So what we want is, we want to identify, okay, this is not working. So, okay, so we'll have x1 will be lambda over p from the analysis before. Theta is q, and lambda is alpha, and also kappa is b squared. So if you make these identifications, then you will basically recover the rank 1 irregular representation of the Virasoro algebra. And you can modify this to go to higher rank by just modifying the alpha, the representation of alpha, and that's actually enough. Beta and gamma should be still in regular representations. So in this way, F will actually act irregularly because of the presence of alpha here, and H will also act in an irregular way, but the others will be regular. So this is from the representation theory point of view. And now I want to come back to the evaluation of conformal blocks, because now we have learned that there is an underlying Kac-Moody symmetry, and we can use operators in irregular representations there. And those are famously known to satisfy KZ equations. So now we can go back and derive the corresponding KZ equations for such irregular operators. And yeah, any questions before I go to that? Okay. Yeah.
Is that like some extra border that you are on top of the
Well, I introduced in the beginning this alpha system, which was just satisfying this kind of Heisenberg algebra, right? So alpha n, alpha m was kind of like this, and those and the beta gammas together will act on the vacuum and furnish the Fock space. So in that sense, okay, maybe, yeah, this alpha here is a different one. So not that you confuse them. Yeah. Okay, so good. So then let me come to the third part and the last part, which is the irregular KZ equations. Okay, so when we talk about KZ equations, we have to talk about conformal blocks. And here, using now these irregular representations, we can actually define these conformal blocks as follows. So you're going to have this wave function or conformal block, which has at infinity one operator in the irregular representations, and everywhere else you have regular highest weight states or corresponding operators, say n minus 1 of them. And then you have a regular state at 0. So these V's are exactly the vacuums I was talking about, the vacuum I was talking about. These are regular. This will be the irregular one, which will be basically satisfying also these conditions under the action of the Virasoro algebra. The others will be all regular. So now if you define this kind of conformal block, where these are the corresponding vertex operators for these regular representations, then this should satisfy a KZ equation. And we can show what it is. So, yeah, we also define basically a function phi gamma c, which is integral over some these Lefschetz symbols. And yeah, and this a here is exactly the function which I had in the beginning. So we have the exponential of lambda over b squared, sum over omega I, or wi, and here you have log wi minus wj plus sum over ij kj over b squared log wi minus zj. So you see that this piece here is exactly the integrand which I had for the Liouville conformal blocks with these degenerate operators with the degenerate weight kj at position cj, and we have these screening charges. Okay, and the corresponding conformal block F is given by phi 0 times this phi gamma. Okay, and this phi 0 is just the piece which one can take out of the integral, so just write it down for completeness. And over 2b squared log zi minus zj. And so this will be our original Liouville conformal block as before, and I want to find the relationship between that and these WZW conformal blocks. So now for M being a tuple of integers, so M1, M2, all the way to Mn, with sum over I, Mi is equal to M fixed. So this M is again some integer which is fixed. We define phi M to be the integral over this A, but now with further insertions of the following form, M1, 1 over Wi1 minus C1, and all the way to In from 1 to Mn of 1 over Win minus Zn, and you have the measure the Mw. So if you compare this to this one, you see that basically this is the previous Liouville conformal block, but just deformed with these further insertions. So you can also think of it in a matrix model language, because these Liouville conformal blocks, if you look at these integral representations, they are just given by, if you look at these functions, they're just given by beta deformed Penna-type matrix models. And you can think of these as resolvents, if you want. So you have the expectation value. This evaluates for you the expectation value of these types of operators, and which is basically given in terms of resolvents. And if you now use this particular definition, you can show that this function is in fact exactly given by these integral representations. So let me just write it down. So then we have the following theorem. So okay, so let psi be a Coulomb vector containing all these phi 0, phi m. Okay, so with sum over them mi being equal to m, then the following holds, namely b squared del zi psi is equal to lambda over 2 hi psi plus sum over j not equal to I omega ij divided by zj minus ci acting on psi. Where this omega here is just the operator hi, so omega ij is hi hj over 2 plus xi yj plus yi xj, and these furnish a representation of SL2C. These will be just the generators of the corresponding Lie algebra, and psi will be a solution of this particular operator equation. And this is exactly the Knižník-Zamolodchikov equation for SL2C with an irregular operator as infinity. So this H, so this lambda is basically responsible for irregularity. If you set it to 0, it's regular. You get the usual KZ equation. But for non-zero lambda, these HI will act kind of in an irregular way. So you have HI acting on this psi is basically Ki minus 2 Mi, right, like this. So yeah, this is the irregular version of KZ equation, and it is basically related to these deformed Liouville conformal blocks, if you want. They will satisfy these types of irregular KZ equations, where this is just the this will act on the ith and jth entry, or ith and jth operator corresponding to the generate operator at position zi and zj, right? So this is how.
Is this what normally is called the dynamical KZ?
Dynamical, no, that will be something else, I think. This is just usual KZ equation
Plus one piece,
plus one piece.
which has a double pole at infinity.
Exactly.
So that's okay.
Yeah.
So some people
Maybe they call it dynamic. I'm not familiar with that literature, but we get it here from these irregular operators. And
do you know how? Do you also obtain higher order poles?
you can also do this for higher order poles. You will get here. You can do it for various cases. You will get various h and powers. You will have powers of z here appearing, and then h's and x's acting here.
So in this case, the irregular representation of the Kac-Moody would be
Higher order. Yes. Higher rank. Yeah, we call it higher degree because rank, you could also use SLN if you want to do Toda theory, and then you will call that the rank. So now it becomes a little bit tricky what you call rank, and there is a rank of the irregularity, there is a rank of the gauge group, so maybe it's better to switch to degree actually for the most general situation. But you will have these types of KZ equations, and you see that this B square is just identified, as I said, well, it's not there anymore, but with this kappa of the KZ. So this will be connecting the two cases. And in some simple cases, we can actually find that these phi m's, these deformed Liouville correlators or conformal blocks, are actually given by certain differential operators acting on the Liouville conformal block. So at the end of the day, this whole differential equation can be re-expressed in some higher order differential equation of the Liouville conformal blocks themselves, and it will be of irregular nature. But so that's it. What I wanted to talk about so far. I mean, we can also give some ideas of the proof here, but I think that will be too technical. So exactly. When we did that, that was in the first paper. In fact, but that was the simple case where this m here was just 1, and we showed indeed that these integral representations satisfy this equation. Now we can also derive it from the Kac-Moody algebra, but before we just derived it from this integral representation, and then you can show actually that this phi 1 is obtained by acting on this phi gamma with a first order differential operator. And together, inserted back here, you will get second order BPZ equation for one screening charge. Because This M here, what is this M? This just tells you how many roots you'll use to lower from the highest weights. So you use basically M roots to go down because you have highest weight representations of SU2, but then you just use these screening operators to go down, kind of. From Kj will be the spin, so Kj half will be the spin of the SU2 representation, and you will go down by M1 to Mn in each of these K1 to Kj. So you will, yeah, that's how Kz usually works. You will have to consider all these SU2 representations, and yeah.
Here you have this Z value are the insertion of
These are the insertions of the degenerate operators, the regular operators.
like one irregular.
Exactly. The irregular infinity is kind of hidden in this expression for A, which is not here, but before it has some exponential pieces, and that's where it is.
But you don't get additional, so your only derivative are with respect to the position.
Yes, we didn't generalize to the positions of the irregular ones, because that you will lose, if you have too many irregular operators, you will lose conformal symmetry and so on.
No,
So
not the position, but there should be like some irregular time.
yes. There will be what I called before this lambda, for example, or C and alpha, and you can derive certain so-called confluent equations, confluent BPZ equations, where you also take derivatives with respect to those, but that we don't do here. So this is just the usual KZ.
And this can also arise from some confluence.
I see.
Yes, this we.
This equation here.
Yes, this one.
Yes.
Of course, you can obtain.
You can basically enrich it by taking derivatives with respect to the C and alpha and so on, you see. You can modify it.
I was thinking about taking KZ,
Yeah.
standard KZ, so without the H term, in which you have more of these ZJs, and then you conference those, and you can create irregular singularity.
Okay. You basically take a limit of those.
Yeah.
I see. As usual. Okay, good.
Well,
Yeah.
so the questions are two different things. One is if you can just answer and sort of get the equation with irregular singularities. The other thing is what is the solution of this? And the solution, I think, is hard, while the equation is hard. Well, what happens normally when you do this kind of conference, you consider the regular case, and so in the regular case, you have the solution will be analytic in some ball. And that's the problem, because when you conference, this both goes down to zero. But you can also consider your solution in a kind of Pac-Man domain, so like a sector. And if you are clever with that, you can actually do conference maintaining the sector finite. And then you actually can manage to build your irregular solution out of the conference of the regular one, as long as you define it in a sector.
It's imaginable, because somehow you have to mimic the fact that you are creating stock sector.
Yes, exactly.
So from physics,
Yes.
it's just by hand.
Yeah, but it is by
It
hand.
was.
Essentially,
Yeah,
what
we
you do,
tried this.
you treat this regular singularity like if it was irregular. So you say, instead of taking a ball, I define it on a sector, and then if you do it cleverly, then you can conference the sector without squeezing it down, maintaining the finite radius.
Yes, exactly.
So this is, for example, what they do when they conference. If you take classical geometric equation.
Yeah, that I know. Yes.
You can do this in sectors.
Yes. That I know. You basically take some double scaling limit there. Yeah. But here, the most important thing is the connection to this Liouville conformal blocks. But yeah, you can obtain these differential equations from probably, as you said, from the ordinary KZ by colliding and then taking certain confluent limits. Yeah. But we didn't derive it that way. Yeah, but you can do it.
But do you have any idea on how it was for connection coefficients? Because for connection coefficients, things change dramatically. I wonder if you have any prescription to get the connection coefficient of an irregular problem, say just one irregular signal from the regular one, or vice versa, which is even more interesting, to split the singularity.
We'll discuss this later. Yeah.
So connections are known, the connection matrices for these things, for these irregular ones, for irregular KZ. Or one can derive them with your techniques, the techniques you mentioned. Or
So maybe we can discuss
Mhm.
later.
Something can be derived. The fact that you have a partial differential equations. Okay, but actually we should have clap to the speaker. So
Okay. Thanks.